The next class of methods that I'm going to describe take a different approach to address the outer distribution action problem. Instead of trying to somehow control the actor, what these methods are going to do is directly repair those overestimated actions in the Q function. So, as we discussed before, the problem is that when you end up picking outer distribution actions in the Bellman backup, you select the ones that have maximal value, and therefore they're the ones that maximally overestimate erroneously. So the picture that I had before in the Monday lecture was that if this green curve represents the true function and the blue curve is your fit, even though the blue curve is a good fit in most places, if you pick the point where the blue curve is maximized, it'll be the one with the largest error in the positive direction. So here's an idea. What if we modify the objective for training the Q function, have our standard Bellman error minimization just like before, and then another term that explicitly seeks to find actions with high Q value and then minimize their value. So notice that mu here is selected so that the expected Q values under mu are as large as possible, and then Q is trained to minimize those values. So intuitively what this procedure should do is find these erroneous peaks and push them down. In fact, it can actually be shown that if alpha is chosen appropriately, the resulting Q function is a lower bound on the true Q function. Now, we can actually work out a better objective than this. The problem with this objective is that it can be a little too pessimistic because we're pushing down all the Q values, which means that the Q function will recover. Will basically never be the right Q function no matter how much data we have. So what we can do instead is we can have this term that always pushes down the Q values, and we can add an additional term that pushes up on Q values in the data set. Now, this might at first seem like a really strange thing because we're combating overestimation, and somehow we're doing this by actually maximizing Q values in the data set. But let's imagine what this procedure will do in practice. If all of the large Q values are for actions that are in the data set, then these two terms should more or less balance out, because mu will select actions in the data set to minimize their value, and then the second term will maximize their value, and the two will basically balance out and have very little net effect. If, however, the large Q values are for actions that are very different from the actions in the data set, the first term will push them down, and the second term will instead push up on the actions in the data set, which means that the next time around, mu is going to select actions closer to the data set. So in a sense, you can think of it as a kind of a feedback process where the more we end up with large Q values out of distribution, the more these two terms together push them back into the distribution. And once they're pushed all the way back, then the two terms more or less cancel out. With this more nuanced version of the objective, it's no longer guaranteed that the learned Q function is a lower bound on the true Q function for all states and actions, but it turns out that it's still guaranteed in expectation over the policy for all states, which is all we really want, because ultimately what we care about is not overestimating the value of the current policy. So this combined objective here I'm going to refer to as LCQL. And what I'll discuss next is how to actually implement this in practice. So the general structure of an algorithm using this idea will be something like this. Update your approximate Q function using LCQL and using your dataset. And then step 2 is update your policy in the usual way to maximize the expected value. And if the actions are discrete, the policy is just the argmax policy, so that's basically exactly the same as in Q-learning. In practice, when you code this up, you wouldn't even have the explicit policy computation in step 2, you would just plug in the max. But if the actions are continuous, then you could have a separate explicit actor, pi theta, and update that actor in the usual way. So in the discrete action cases, this really does look like Q-learning with 2 additional terms. In the continuous action case, typically you would do this as a Q function actor-critic algorithm. So the actor training in that case is exactly the same as in a regular actor-critic method. The only thing that changes is the loss function for the critic with the addition of these 2 terms, the pushing down and the pushing up term. So this is the critic objective. Now, in practice, if you want to actually implement this, what you would do is you would added a little regularizer for mu, let's call it R of mu. And for appropriate choices of that regularizer, it turns out that there are very convenient ways to implement the subjective that don't require actually computing mu directly. So a very common choice for this regularizer is to use the entropy of mu. This essentially amounts to saying we want to get mu to have high entropy, and we wanted to capture actions with high Q values. So it's a kind of a maximum entropy regularization. It turns out that if you do this, the optimal choice for mu is proportional to the exponential of the Q values. Furthermore, it turns out to also be the case that the expected value under mu of the Q function is the log sum exp of the Q values. So that's kind of a convenient property, and if you have discrete actions and you use this maximum entropy regularization, then you don't even need to construct mu explicitly. You can simply minimize the log sum exp of the Q values at every state. So that's very convenient. So for discrete actions, just literally calculate this quantity directly. For continuous actions, you could use importance sampling to estimate the expected value under mu of the Q function. So you could sample actions either uniformly at random or from the current policy, and then reweight them by using the exponential Q, by basically leveraging the fact that the optimal mu is proportional to the exponential Q, and then use that to estimate this expectation. And both of these are perfectly valid choices. So for discrete action, just directly using this log sum exp formula tends to work really well. For continuous actions, something like importance sampling tends to work pretty well. And even though it's importance sampling and we would ordinarily be worried about high variance, remember that here we're not multiplying together importance weights over many time steps, it's just for one time step. So that actually works decently well. So that's basically what you would need to implement CQL. You would use the general design on this slide to implement the critic update, and then the structure of the algorithm would alternate between updating the critic and updating the actor if you're doing continuous actions, or if you're doing discrete actions, just use the argmax policy on the second line of the critic objective.